Hello everybody. In this video, we're going to review expressions. So an algebraic expression is a mathematical phrase that contains numbers, variables, or the product of numbers and variables. The biggest thing to remember about expressions is that there are no equal signs. If you have an equal sign, then you have an equation. Here, there are no symbols like that with equals or inequalities, because if you had an equal sign, that would be an equation, and if you had an inequality symbol, then you would have an inequality. So the first type of algebraic expressions that we're going to look at and review today are radicals. So to be able to simplify a radical, we learned about prime factorization. And the method that we focused on this year was the division of primes method, which we called the birthday cake method. And so to do prime factorization using birthday cake, you take the number that you want to prime factorize, and so that's 18. And that's going to go in the bottom of my cake. The smallest prime number that goes into 18 is 2. 2 goes into 18 9 times. The smallest prime number that goes into 9 is 3. 3 goes into 9 3 times. The smallest prime number that goes into 3 is 3. 3 goes into itself once. When you get to 1, you're done. That's the candle to your birthday cake. So the prime factorization of 18 is 2 times 3 times 3. So I'm getting those numbers from these outside numbers right here. And if you look at them, 2 times 3 is 6. 6 times 3 is 18. So this is how you can multiply to get to 18 using only prime numbers. We use prime factorization to simplify radicals. So if I look at this next example, we want to simplify the square root of 40. If you try to do the square root of 40 in your calculator, you're going to get a decimal. And in mathematics, we like exact answers. And when we get a decimal, sometimes it can be an approximate. So to keep this in radical form, we are going to do the prime factorization of 40. The smallest prime number that goes into 40 is 2. 2 goes into 40 20 times. The smallest prime number that goes into 20 is 2. 2 goes into 20 10 times. The smallest prime number that goes into 10 is 2. 2 goes into 10 5 times. And the smallest prime number that goes into 5 is 5. 5 goes into itself 1 time. When you get to 1, you're done. That's the candle to your cake. Again, I'm looking for pairs of numbers to be able to leave my square root symbol. And so here I have a pair of 2's that can leave. This 2 doesn't have a pair, so that 2 is going to stay inside my square root symbol. And this 5 doesn't have a pair, so that 5 is going to stay inside my square root symbol. When you have more than one number staying inside your radical, you're going to multiply them together. 2 times 5 is 10. So the square root of 40 simplified is 2 square roots of 10. Let's try this process again with the second example. In this second example, I have 5 square roots of 27. 5 is a coefficient out in front. So that's going to be a part of my answer. So I'm going to go ahead and write it down so I do not forget about it. And then I'm going to do birthday cake for 27. So I'm going to do prime factorization. The smallest prime number that goes into 27 is 3. 3 goes into 27 9 times. The smallest prime number that goes into 9 is 3. 3 goes into 9 3 times. The smallest prime number that goes into 3 is 3. 3 goes into itself 1 time. When you get to 1, you're done. That's the candle to your cake. Here I'm looking for pairs of numbers to leave my square root symbol. And so I have a pair of 3's that can leave the square root symbol. This 3 does not have a pair, so that 3 is going to stay inside. The pair of 3's that we found outside are going to get multiplied by that coefficient of 5 that was already there. 5 times 3 is 15. So 5 square roots of 27 has been simplified to 15 square roots of 3. We can add and subtract radicals, but in order to be able to do that, we must have like terms. For square roots, you will have like terms if they both are square roots and if they have the same radicand. Remember, a radicand is the number inside the square root symbol. So on this example, I have 2 square roots of 6 plus 3 square roots of 54 minus 3 square roots of 24. Right now, I do not have like terms. So I'm going to simplify to get like terms. And so if I try to simplify 2 square roots of 6, I'm going to bring down the 2 because that's my coefficient. And I'm going to do birthday cake for 6. Oops. So the smallest prime number that goes into 6 is 2. 2 goes into 6 3 times. The smallest prime number that goes into 3 is 3. 3 goes into itself once. So I don't have any pairs here, so that tells me that the square root of 6 is already simplified. I'm going to do the same thing with the next term. So I'm going to bring down my plus sign and my coefficient of 3. And now I'm going to do birthday cake for 54. The smallest prime number that goes into 54 is 2. 2 goes into 54 27 times. The smallest prime number that goes into 27 is 3. 3 goes into 27 9 times. The smallest prime number that goes into 9 is 3. 3 goes into 9 3 times. And then 3 goes into itself once. So I'm looking for pairs of numbers to leave the square root symbol. And here I have a pair of 3's that can leave. They're going to get multiplied by that coefficient of 3 that was already out front. This 2 and this 3 do not have any pairs. So they're going to stay inside the square root symbol. And then I'm going to bring down my negative 3. And I'm going to do birthday cake for 24. The smallest prime number that goes into 24 is 2. It goes in 12 times. The smallest prime number that goes into 12 is 2. It goes in 6 times. The smallest prime number that goes into 6 is 2. It goes in 3 times. And 3 goes into itself 1 time. So again, I'm looking for pairs of numbers to leave the square root symbol. I have a pair of 2's that can leave. And then this 2 and this 3 do not have a pair, so they are going to stay inside my square root symbol. So I'm going to simplify this a little bit and see what I'm working with. So I'm going to bring down my 2 square roots of 6. 3 times 3 is 9. And 2 times 3 is 6. Negative 3 times 2 is negative 6, and 2 times 3 is 6. So all we've done so far is simplify. And when I look at these, all of my terms have the square root of 6. So these are like terms. So I can add and subtract these terms. To do that, we add or subtract the coefficients and we keep the square root and the radicand. So 2 plus 9 is 11. 11 minus 6 is 5. So my answer is 5 square roots of 6. To multiply radicals, you multiply the coefficients together and you multiply the radicands together. And then you want to simplify. So on this first example, I have the square root of 10 times the square root of 2. So that's going to give me the square root of 20 because 10 times 2 is 20. Once you find the square root, or once you multiply, then you want to simplify. So the smallest prime number that goes into 20 is 2, goes in 10 times. The smallest prime number that goes into 10 is 2, goes in 5 times. And 5 goes into itself 1 time. When you get to 1, you're done. That's the candle to your cake. We're looking for pairs of numbers to leave the square root symbol. Here I have a pair of 2's that can leave. 5 does not have a pair, so 5 stays inside the square root symbol. So our answer is 2 square roots of 5. Let's try that again with the second example. I'm going to begin by multiplying the coefficients. Negative 2 times 4 is negative 8. 15 times 3 is 45. Now I want to simplify negative 8 square roots of 45. Negative 8 is the coefficient out in front, and then I want to do the prime factorization of 45. The smallest prime number that goes into 45 is 3. It goes in 15 times. The smallest prime number that goes into 15 is 3. It goes in 5 times. The smallest prime number that goes into 5 is 5. It goes in once. When you get to 1, you're done. That's the candle to your cake. I have a pair of 3's that can leave the square root symbol. This 5 does not have a pair, so that 5 is going to stay inside. Negative 8 times 3 is negative 24. So my answer is negative 24 square roots of 5. So that is what we learned about radicals. And now we're going to review what we learned about polynomials. So with polynomials, we can classify them by their degree and by the number of terms. Remember, the degree is the highest exponent, and the number of terms is how many terms you have. So if we have just something that doesn't have an exponent, so the exponent is 0, the highest exponent of the variable, I should say. So if we just have a number with no variable, then the variable exponent would be 0, and we would have a constant. If the highest exponent is 1, then we would have something that is linear. If we have something with the highest exponent of 2, then it's quadratic. If the highest exponent is 3, then it's cubic. And if the highest exponent is 4, then it's quartic. If we have just one term, then we have a monomial. If we have 2 terms, then we'll have a binomial. If we have 3 terms, we'll have a trinomial. And anything with 4 or more terms, we could just call it a polynomial. Just like with radicals, if we want to add polynomials together, we must have like terms. In this case, like terms have the same variable raised to the same exponent. So when I look at these parentheses, I'm looking to see if there's anything to distribute in front, and there isn't. So I can go ahead and drop the parentheses. Same thing with the next one. There's nothing to distribute out in front, so I can drop those parentheses as well. From here, I can combine like terms. So 3x and 5x are like terms. 3x plus 5x is 8x. -1 and -4 are like terms. -1 minus 4 is -5. And then x squared, or -x squared plus x squared are like terms. -x squared plus x squared is 0, so these cancel. So my answer is 8x minus 5. If I wanted to classify this polynomial, my highest variable exponent is 1, so that makes this linear. And then I have 2 terms, so it's a binomial. So this would be a linear binomial. Same thing with subtracting polynomials. Here, so this should be a minus sign. That will be fixed on yours. You also need to have like terms. So when I look at this first set of parentheses, there's nothing to distribute here. And so I can just go ahead and bring down those. So 5x squared plus 7x minus 6. For this second set of parentheses, I have this negative sign out in front. And this is really like a -1. And so I need to distribute that to everything in this second set of parentheses. -1 times 5x, sorry about that, is -5x. -1 times 6 is -6. And -1 times -4x squared is +4x squared. Now that I've distributed that negative sign, I can go ahead and combine like terms. 5x squared plus 4x squared is 9x squared. 7x minus 5x is 2x. -6 minus 6 is -12. So this is my answer. If I wanted to classify this polynomial, my highest degree is 2, so that would make this quadratic. And then I have 3 terms, so it's a quadratic trinomial. And then finally, we have multiplying polynomials. So with this first example, I can use a distributive property. 8 times x is 8x, and 8 times 6 is 48. So these are not like terms, so that is my answer, 8x plus 48. And if I were to classify this polynomial, this would be a linear binomial. Linear because my highest variable exponent is 1. Binomial because I have 2 terms. And for this last example, I have a binomial being multiplied by a binomial. So 2 terms being multiplied by 2 terms. We learn to multiply binomials by using the area model. So, I'm going to take one binomial and I'm going to write it down the side. And I'm going to take the other binomial and I'm going to write it across the top. Next, I'm going to multiply each square together. So 4x times 5x is 20x squared. 4x times -6 is -24x. 5 times 5x is 25x. And 5 times -6 is -30. So I have 20x squared minus 24x plus 25x minus 30. From here, I can combine like terms. 20x squared doesn't have a like term, so I'm going to bring that down. -24x plus 25x is 1x. And -30 doesn't have a like term, so I'm going to bring that one down. If I were to classify this polynomial, this would be a quadratic trinomial. Quadratic because the highest exponent is 2. Trinomial because we have 3 terms.